Um, and okay. So log linear models, and so my point of view on this is that it's logistic regression generalized to structured input and structured output. So in a logistic regression, the input is an x bar that's a real valued vector, and the output y is binary. But we we want to solve much more general supervised learning problems. We want to allow x to belong to any space x, and also, in fact, y to belong to any space y. And so, example, x could be a sentence like he sat on the mat. And y would be maybe a list of parts of speech. So pronoun, verb, preposition, article, and noun. So this is a supervised learning problem. This is a classifier learning problem where we have training data, which consists of pairs, and the x is an English sentence, and the y is a sequence of part of speech tags. And a part of speech tag is a label for the category of a word. And so this is a natural language processing problem that is easier than, say, figuring out the complete grammatical structure of a sentence. This is really figuring out the grammatical role of each word without figuring out how the grammatical roles interplay with each other. And so, in traditional machine learning, so there's research on generalizing from two-class output to multi-class output. And there's also regression methods where you can have a real valued output, but we want to go far beyond this. We want to allow inputs and outputs to be not real valued. This input is not even a vector because different inputs can have different lengths. And then this output is, it's not, this is not multi-class. There isn't some fixed number of labels and you're choosing one label in that fixed number. There's so here the set X might be the set of words, and then the star, the set of all sequences of arbitrary length. And same thing for Y, it's the set of tags, star. So this is language notation. The only assumption really I'm going to make about now is that this set Y is, well, I guess I'm going to assume it's finite. So technically this set is not even finite, it's countable because the tags could be of arbitrary length. But supposing that I limit my sentences, say, to be 20 words long, then the Y set becomes finite, and that's the only thing that I need to assume. So yeah.
So your X is words, and Y is tag.
Actually, X is a sentence. It's pretty important to for me to use some precise terminology here. So in this case, so one input is one sentence, and one output is one label, and that label is a string or sequence of tags.
So if I want to invite, say, the relative occurrence of words in that those sentences concluded as part of this regression, how do I understand that?
So was the question? So what I'm going to explain in just 1 minute is how to represent x and y. And as part of representing x, I'm going to be able to represent things like how many times does a particular word occur in x. And so on. Is that the sort of question you're asking?
Or relative occurrences.
Yeah. Okay. So I think I'll be able to answer that in a minute. Okay. So. So here's the model. So probability of y given x, and for some reason I'm changing my notation now. So instead of using beta for the parameters, I'm using w for the parameters. W stands for weights. So probability of y given x and w is there's a normalizing term, which I'll just call z of x and w. I'll talk about that in a minute. And then up here, I have an exponential of sum over j of wj. So this is fj, capital Fj, of x and y. Okay. So I'm putting up this expression now so as to show you immediately how this looks a lot like logistic regression. So this is an exponential of a linear function, and the probability is essentially the exponential of a linear function. So it looks a lot like logistic regression. And logistic regression is going to turn out to be a special case of this. But you should have a lot of questions, like, what is this denominator z? And then what are these functions fj, which are functions of x and y? And so maybe, so I'll give the quick answer to the question of what's the denominator first. So this is sort of just the formal answer. The z of x and w is the sum over all y prime of exp of sum over j, wj, fj, x, y prime. So here we have the numerator, which refers to x and y. X and y come from here. And then here we have a sum over all y prime of the numerator x and y prime. So I plugged in y prime instead of y. Can somebody, and I said that the only thing that I really need to assume about the label set y is that it's finite. And the reason I need the label set y to be finite is here I'm summing over everything in the label set. So that's only well defined if I'm summing over a finite set. But can somebody explain why this has to be the formal definition of z? Without this having really any particular intuitive meaning, it still mathematically has to be this, and why?
Normalization.
Sorry?
Normalization to your probability.
Normalization. So can you explain a little bit more?
Because of the denominator in summation of all of it.
Yes. Yes. So for any x, one of the y's is going to be the label. So when I sum over all the y's, the sum of those probabilities has to be 1. And and I get those probabilities by having different numerators. So if I sum the numerators over all y, and then divide each of those numerators by the denominator, the result has to equal 1. This is just the most basic principle of probability is that if you have a set of mutually exclusive events, then the sum of their, and exhaustive, then the sum of their probabilities is 1. So just from a formal point of view, the denominator has to equal the sum of the numerators. So denominator equals sum of numerators, and that's the z. So I'll come back to this, but that's the first level explanation of why z is the way it is. And then these big so each fj of x and y is called a feature function. It plays the role of a feature. In logistic regression, I had wj times xj, but here my x's are not necessarily vectors, so I couldn't multiply wj by xj. Xj might not even exist, but this function f, it plays the role of a feature and is a function, so I call it a feature function. Fj is so function from x cross y to the reals, and there's a so I want to so notice, so if fj of x and y is greater than 0 and wj is greater than 0, then p of y given x, w, is increased. Compared to fj of x and y equals 0. The intuitive meaning of a feature function, if it has a positive weight, is that the bigger the value of the feature function, the more this y is compatible with this x. So fj of xy equals degree of compatibility between x and y. So if you have, if for a particular x and a particular y, the feature function has a big number, and you have a positive wj, then that y is going to have a high probability. Okay, if the feature is negatively correlated, then so if we had, if wj was positive and then fj had a negative value, then the bigger the negative value, the lower the probability of y given x.
But that's not what we expect, right?
Huh?
That's not what we expect at all. What I mean by negative correlated is that although the value is, the actual feature value might be What I mean is that there are cases where the feature, maybe in that case, like really the magnitude is a problem, but not really the sign.
Mhm.
So in other words, the higher maybe the feature, the lower the feature value is, maybe it contains more signal that correlates to the final probability.
Okay.
And this formula seems to be then actually removed those cases rather than promote.
It is possible for the weight Wj to be negative. And if the weight Wj is negative, then a big value for the feature function is going to reduce the probability to y.
How does the feature, the weight is set? Or how
Okay.
do you learn the weight?
Yeah. So I'm feeling a bit of a chicken and egg problem in talking about log linear models because everything's connected. These weights, which are the equivalent of the betas I had before, they're the parameters, and we're going to have a learning algorithm for them. And so what we actually do is we define feature functions, and then the feature function, we define a feature function that measures some property of x and y, and then the learning algorithm is going to learn whether or not that probability has an affinity with y being more likely or has an affinity with y being less likely.
So is the arrangement telling you if it's more likely, less likely, or is it the value of the function?
Once the value of the function is defined and it's predefined, then it's the weight that actually tells us. But when we define, when the human defines the function, then the human is going to define functions that that he thinks or she thinks is are likely to have affinity. Maybe it's easiest if I sort of move on to trying to show some examples. Okay, so supposing x equals sentence, y equals tag sequence. So this is the same part of speech example. Then I might have fj of x and y would be, x starts with a capitalized word, or well, all sentences start with capitalized words, so that's not a good. Okay. So just second word is capitalized. And second tag is proper noun. So fj of xy is second word is capitalized and second tag is proper noun. So, feature functions are real valued, but a very common special case of a feature function is that they're 0, 1 valued. And so here's a feature function that has a 0, 1 value. The second word of the sentence starts with a capital letter, and the second tag is proper noun. And chances are that when we train this model, we're going to find that the weight Wj is large and positive. So what that means, what that's going to do is it's going to say that everything else being equal, if this feature function is switched on, then the tag sequence y is more likely. So here's another feature function. So f 14 of x and y is first word is capitalized, and first tag is proper noun. I'm not writing this. First tag is proper noun. So, this is also a 0-1 feature that we can measure about any sentence and any tag sequence. First word is capitalized and first tag is proper noun. But there are going to be lots of sentences where there are going to be lots of XY pairs where Y is the correct answer for X, but this feature function is 0. Those are going to be sentences which have a first word which is capitalized, but that first word is not a proper noun. And so the weight W14 that we learned for this feature is going to be pretty small. But the weight, if this is feature 15, the weight W15 that we learned for this feature is going to be pretty big. Because if this feature is true, then Y tends to be the correct answer for X.
So this is a Boolean function.
Okay, so these examples are Boolean functions. And Boolean functions are a special case of real-valued functions. And in general, feature functions are allowed to be real-valued, but they're often Boolean. Sorry? And they're allowed to be positive or negative. They're allowed to take on any real value. I mean, for many problems, it's hard to think of sensible real-valued feature functions, but the formalism allows for them. And here's okay, F16 of X and Y is length of Y minus length of X. So that's an example of a real-valued feature function. The length of Y minus the length of X. And supposing that X was an English sentence and Y was a French sentence, then French sentence, when you translate from English into French, the translation tends to be longer than the original. So length of Y minus length of X is, it tends to be positive for correct translations. And if length of Y is less than length of X, then Y is probably incorrect. So if we were trying to learn a log linear model to do translation, then this is a feature function that would probably end up with a positive weight. And this is a real-valued feature function. So for any application of log linear models, including conditional random fields, the first thing you have to do is define all your feature functions. And and then the learning process is to find weights for the feature functions so that when a feature function is positive and the weight is positive, then the Y is more likely. And when the product Wj, Fj is negative, then the Y should be less likely. Okay. Let me try to be a little okay.
Typically you use that a lot of a long list of Boolean features for conditional method evaluating the training. Right? That's kind of what typically
Yes,
what
yes.
you do. And what is the empirical implication of including those kind of real value features with lots of our binary features? Is it having like any real value features, does it tend to make that feature to be rated higher or lower, or no implications whatsoever, or any kind of empirical, you know,
I-
those?
I don't think there's any particular implication of having real-valued and binary feature functions versus having just binary feature functions. I think it's that some problems naturally lend themselves to binary feature functions. You may not have any real-valued functions at all. And other problems may lend themselves to both or lend themselves only to real-valued feature functions. I think it just depends on the problem. And I certainly wouldn't try to create feature functions of one type or the other type if they weren't natural.
It's kind of whatever that feature, the natural way of representing that feature should be okay.
Yes.
So we assume that, you know, your earlier suggestion of normalization for each feature does
Uh-huh.
range is applicable.
Yeah, so it could still, yeah.
Given that there is no much of other side effects.
Right. And even the normalization of the normalization of the range of the feature function, that's important if you're going to be doing stochastic gradient with a single learning rate lambda or a single step size lambda. It may be less important if you're going to use a different training algorithm. So let me. Okay. So let's look. Common ways of constructing feature functions. So let a of x be a function of x. And then we can define fj of x and y to be equal to a of x indicator of y equals v for all v in y. So so if capital Y is the space of all alternative values that we might be trying to predict, then we can create one feature function for each of those values v, and then that feature function is going to have the value a of x if y equals v, and it's going to have the value 0 if y is not equal to v. And so then if we have our formula, so p of y given x, w is, so there's a normalizing constant, x sum over j, wj, fj of x and y, then we're going to have, so this will equal this. So what we're going to end up with is we're going to have a parameter wj which gets multiplied by a of x, and we have a different parameter wj for each value y. And so with all those parameters, we can learn the affinity of a of x for each different y. And and so this is how you would translate a conventional feature. So a conventional feature is a function of just x, and this is how you translate it into a feature function, because a feature function has to be a function of x and y. But the simplest thing is to have just really one copy of the conventional feature for each value of y. Maybe I should try to show how logistic regression is a special case of this.
So there should be some sort of correspondence, for example, in your part of speech labeling, right? When you have a capitalized word, that it should end up being a proper noun. So if you were looking through your entire training set, and every time you have a capitalized word, there's a certain frequency that it ends up being a proper noun. So that weight, or the feature function there, or maybe it's the weight, should eventually somehow match that frequency. And you're learning the frequency there, of how often that occurs.
Yeah. I think I agree. I'm not sure how to state that precisely. In order to go into the part of speech example in more detail, I need to get onto conditional random fields. Yeah. Maybe that's where I should go now, and I shall come back to log linear models if if I need to say something about them in general. Okay. So with we have x belonging to a general x, y belonging to a general y. And now with a linear chain CRFs, which are the most common sort of CRF and the sort I'm going to be talking about, we have that x is an input sequence and y is an output sequence, and the simplest case is where the output sequence is of the same length. And so part of speech is an example of this, but another example is hyphenation. So the input might be, x equals beloved, and then the output would be y equals 0, 0, 1, and then maybe 0, 0, 0, 0, 0. So, and because the way this word can be hyphenated is b hyphen loved. And, I'm not sure if it's really legal to have a hyphen after the V. Certainly it's not legal to have a hyphen anywhere else in this word. And so the input here would be a sequence of letters, and then the output would be a sequence of bits. And each bit is going to indicate whether or not a hyphen is legal whether or not a hyphen is legal immediately after the corresponding letter. Yeah?
Well, it just seems like a kind of crazy, kind of strange example because the last bit is kind of just a placeholder.
Oh, yeah, so the last bit is just a placeholder. And in fact, I'm going to I'm going to use a placeholder for the position before the first position, the position after the last position, because that's going to make describing some algorithms simpler. But in this particular case, actually, we know maybe the rules of English say that you can't hyphenate after the last letter. And the rules of English, I think, also say that you never hyphenate after the first letter. Well, actually, maybe you do, like amoral. But maybe you never hyphenate before the last letter. But so this is a representation. So actually, what that illustrates is that there are some y's in the output set y that should have a low probability regardless of the input x. But that's something that I can try to learn from the data rather than pre-specifying. So actually, so let's look at so every feature function fj of x and y. One feature function might be, number of non-zeros in y divided by the length of x. And so here it would be 1 out of 7. And we could use this feature function to learn what is a typical fraction of hyphens in a word, because one hyphen out of 7 is probably below average, and having a hyphen after every second letter is probably above average, and there's some intermediate density of hyphens which would give the y string the highest probability. So for linear chain CRFs, there's a restriction on which feature functions I'm allowed. And this is that. So feature function j, for any j, and it's a function of x bar and y bar. And now I'm going to use the bar notation to mean sequences. It's going to be the sum over I. So I ranges over the sequence. So from I equals 1 to the length of the sequence of little fj of yi minus 1, yi, x bar, and I. And then so an example of a feature function, so feature function 18, little feature function 18 might be of yi minus 1, yi, x bar, I might be, so I equals 2 and yi minus 1 equals 0 and yi equals 1 and x1, x2 equals am. Yeah. So forget this for a minute and just think about this as an example, another example of a feature function. So I'm paying attention to position I equals 2. So then yi minus 1 would be y1, yi would be y2. So I'm paying attention to the first two labels in the string, the first two tags. And those first two tags are 0 and 1, according to this feature function. And actually, let me make that be 1 and 0. And then I'm paying attention to the first two letters in the word, and those first two letters are AM. So when you have the first two letters AM, the tags 1, 0, is that plausible tags for the first two letters of the word being AM? Well, you think of words that begin with AM. There's amoral, which you probably can hyphenate like this. And then there's
Ameliorate?
what?
Ameliorate?
Ameliorate, where you could have a hyphen, and then there's one which I can think of where you wouldn't have a hyphen. I think amatory is a word, it means to do with love. So sometimes you're allowed a hyphen after the A, and sometimes you're not allowed a hyphen after the A. And but probably mostly you are allowed a hyphen after the A. And so with this feature function, then you'd learn a weight for it that was positive, and what that positive weight would be meaning would be that any tag sequence Y that starts out 1, 0 has everything else being equal has a high probability. So every XY pair where X starts out AM and Y starts out hyphen, no hyphen, is a higher probability XY pair. Yes?
I have a question. Because this feature value depends on the label, so it's like different from the traditional text categorization. The feature value
Yes.
term frequency does depend on the label.
Yes. So
When you change the label,
yes.
depending on it.
Yeah. So this is what you said is exactly right. And the idea of feature function is a novel idea for machine learning, and it's an idea that it can be hard to get your head around at first, because we're so used to thinking of features as being properties of the input X. But when we have a very large output space Y, then we really need to talk about properties of the output space Y also. And rather than thinking of a mapping from X to Y, we should think of XY pairs and then working out whether the XY pair is a good pair or a bad pair. Let me try to sketch yet another example, and this will be an example of a log linear model that is not a conditional random field. So consider the problem of multi-label supervised learning. Who knows what the multi-label problem is? It's different from the multi-class problem. Okay. So the multi-class problem is when you have an input X and you want to predict a label Y, and the Y comes from a set that is bigger than a binary set. So if you want to classify somebody as freshman, sophomore, junior, senior, that's multi-class. But multi-label is when you want to classify your X as having 0 or more labels. So each X has 0 or more labels. And so, for example, each document, maybe you want to map it onto some subset of sports, business, politics, TV. So you have some the classic document categorization problem. You have documents and you want to assign them to categories. But each document can belong to more than one category. So if you have a document about Mike Tyson having tax problems, then that might belong to the sports category and the business category and the politics category if there's a political aspect to his tax problems. So the multi-label supervised learning problem is learning to assign X's to 0 or more labels. And so if you have 10 classes, then how many possible combinations of labels are there? Two to the 10. So 2 to the 10 combinations, which is about 10 to the 6. No, 10 to the 3. 1024. And if you had 20 classes, it would be about 1 million. So if you had 20 classes and each document was allowed to belong to 1 or more classes, then there would be some combinations of classes that chances are you have never seen in your training data. But you'd still like to be able to predict that combination for a test document. And so one way to attack this problem would be to build 10 separate binary classifiers, and then to just classify each document as sports or not sports, business or not business, and then to allow the document to belong to all the labels of the classifiers that said it belonged to that corresponding class. But can you see a type of information? So supposing you had 10 classes, you built 10 separate classifiers. There's a source of information that's in the training data that you're not going to be able to capture using those 10 classifiers. What information are you not going to be able to capture directly?
Wouldn't that be the correlation between the labels?
The correlation between the classes. And so if you use a log linear model approach, then you can have a feature functions. So feature function F19 of X and Y might be sports belongs to Y and business belongs to Y. And so notice this is a feature function that depends on Y and doesn't depend on X at all. But you can still learn a weight for it from your training data. And if you learn a positive weight for this feature function, it's going to be saying that everything else being equal, sports and business go together. And if you learn a negative weight for it, it's going to say everything else being equal, if it's a sports document, then it's not also a business document, and vice versa. If you were using a log linear model with feature functions, really the key thing is if you were using feature functions to attack this multi-label problem, then you can directly learn correlations between the different parts of your class. And that's why I used the word structured input, structured output. So here, so we have 1,024 labels, but those 1,024 labels have internal structure because they're subsets. And then we can use feature functions to represent that internal structure, and then we can learn we can learn which structure cases are favorable and which structure cases are unfavorable.
But in this case, you don't need to learn more than just the binary pairs for feature functions, right? You wouldn't want to have possible combination as a feature function?
Well, that's, I think that's going to depend mainly on your training set size. So if you think of, so if we have 10 classes, then I guess there are 10 choose 2, 45 possible pairs. And so I could have 45 feature functions like this. And if I have a lot of training data, I probably have enough examples of each pair to learn a reliable preference for or against that pair. But if I considered triples, like sports and business and politics, then there are, I guess, 10 choose 3 of those, which, I don't know, would it be 45 times 8? In the 300s. So there are a lot more triples, and so I'm going to have less reliable evidence from the training data about each of the triples. And so it's going to be a judgment call how many feature functions I want to put in my model.
So you should be able to capture that by looking at the sparsity of the feature functions.
Yes. So what I could certainly do is I could create one feature function of each triple of pairs, and then I could see for each of those triples how many times it occurred in the training data. And if it only occurs 0 or once in the training data, I might not create a feature function for it because the parameter that I would learn for that feature function would probably be unreliable. It would be overfitting the training data. So, in fact, for conditional random fields in particular, but I think also for log linear models in general, there are quite a few papers that have been published on the topic of feature selection, and by that they mean feature function selection. Yeah. So this is a example of an application of log linear models that is not conditional random fields, because the labels here, the x's and the y's are not sequences. And it's also an example of how it can be useful to have a feature function that depends only on the y's. Most feature functions will depend on the x and the y, and you'll be using them to learn some compatibility between x and y. But it's also useful just to learn an internal compatibility in the y. So is this y overall a likely y or an unlikely y? All right. So that was multi-label supervised learning. And okay. Oh, just so going back to this expression. Yes.
So related to this whole multi-class learning problem, is there a generalization of logistic regression for learning multi-class?
Yes, absolutely. So the generalization of logistic regression to the multi-class case is called multinomial logistic regression. And but then, and that's not mentioned in here because multinomial logistic regression is a special case of general log linear models. And so I just, I didn't put in that intermediate stage. But multinomial logistic regression certainly exists, it's well known, and is very useful in practice. What the recent research in machine learning has done is go beyond multinomial logistic regression into, for example, so multinomial logistic regression would be a good way of classifying documents into multiple classes. But a log linear model is a good way of doing something more sophisticated, which is multi-label classification of documents.
But if you're using these general non-linear models
Yeah.
for doing what do you call multinomial linear regression?
Yes.
There must be some penalty.
Must some
Is there some penalty for doing that?
penalty?
Performance or what? Learning rate?
No, there isn't a penalty because because it just simplifies, the mathematics just simplifies. It's a special case, but so maybe a better way of saying it is that log linear models are a generalization of multinomial logistic regression. So if you need that generalization, you can go and take that generalization, but if you don't need it, you stick with multinomial logistic regression.
I mean, I guess, would you use the same software?
Well,
Same implementation?
for standard logistic regression and for multinomial logistic regression, that's very mature from a software point of view, and it's built into most existing packages. But if you have an extremely large-scale problem, the sort of problem that only computer scientists think about and statisticians don't think about, then using stochastic gradient would be a good way of implementing it yourself. And there was a PhD thesis at Carnegie Mellon University a few years ago by somebody called, I think, Andrew Komarek. Certainly his advisor was Andrew Moore, so Komarek and Moore. And they've published a couple of very good papers specifically on very efficient large-scale algorithms for doing logistic regression. But that was a few years ago, and more researchers now are interested in efficient algorithms for the more general case of log linear models or conditional random fields. But for large-scale logistic regression, there's some very good algorithms for that, including for the multinomial case. Yes?
In what system can labels be weighted?
Well, you can certainly learn weights for the labels in the sense that if some labels are more common in your training data than others, then you can have a feature function that refers to, that just is 1 when that label is present and 0 when it's absent. And then the weight, the parameter you'll learn for that feature function will essentially be the bias in favor of that label. And then, so you can learn that some labels are preferred overall. What you can also certainly do is you can have weights on the training examples. Lots of machine learning algorithms can be extended pretty easily so that some training examples have higher weight than other, and that certainly applies to all these log linear models, but it's not something that I'm going to mention. Okay, so. I feel that I've been going around in circles a bit talking about log linear models and conditional random fields. It definitely is something that it's a different way of thinking. Okay. So my model is probably a y given x w is normalizing function zxw, and then exponential sum over j parameter wj times fj of x bar of x and y. And when I was talking about the multi-label example just now, I pointed out that you can have useful feature functions that don't depend on x, that only depend on y. So now here's a question for the audience. If you had a feature function that only depended on x and didn't depend on y, would that be useful? feature function that only